Hello students, welcome to this second lecture on calculus of variations. In this lecture we are going to discuss two main topics. One is the variational problem and the necessary condition for existence of extremum. So both the things we'll discuss here. Now first, what is a variational problem? Basically, a variational problem is a problem of optimization that involves generalized coordinates or generalized variables. As I told you in the last lecture that in calculus of variation we are basically dealing with functionals, and a functional is nothing but a function of function. Here you can see this in this situation, in general I told you that a function can be written like this: f as function of x, y and y dash, and you can further extend to y double dash, y triple dash, etc., and so on and so forth. So usually in functions we have variables like f is a function of x, y. Then I can consider that x, y coordinates are there, and if I take function of three variables, suppose f, x, y, z, then I can consider these are the three coordinates. But these are simple two-dimensional or three-dimensional coordinates. But in this situation, the situation is not like that. Here x is a function, x is a variable, and y is depending on x. Similarly, y dash is also depending on x. So, but in a functional, these y and y dash are also behaving like variables. So y and y dash in fact will be called the generalized variables. And in mechanics we'll also study these kind of situations. So there we'll call the generalized coordinates. There will be generalized velocities in place of this. If it is the displacement coordinate, then if we take the first derivative, that becomes the generalized velocity, the generalized acceleration, etc. So if a problem of optimization involves generalized variables, then such a problem is called a variational problem. To have more understanding regarding this, here we are considering these three numericals. The first statement is the very basic one, the problem of finding the minimum distance between 2 points on a plane. Problem of determining a curve of minimum distance between 2 points. I have already mentioned that suppose you are having 2 points here. Suppose you are having 2 points A and B here. Then you can see you can join these 2 points through various curves. You can join these 2 points through various curves. Suppose here is point A and here is point B, then you can move from A to B by various ways, by various curves like this. But there will be one curve that through which the distance will be minimum. So suppose this is curve C1, this is C2, this is C3, and you can have infinite number of curves between these 2 points. So now the question is, find the shortest plane curve joining 2 points A and B, and to find the curve y equal to yx, for which the this functional, in fact the along with this integral, we call it as a functional, and generally we denote it by I of y, because here y is the function of x. And then further generalization of variables involving the derivatives of y. Okay, so in this situation, this is the functional here, and we have to find the value of y along which this I is minimum. Means this functional is minimum. Functional means this distance between two curves, between 2 points A and B is minimum. So this is a description of this problem, one of very fundamental basic problem in calculus of variation. So this is one variational problem. In the same manner, a very famous problem that was first time posed by Galileo in 1630. This problem, Parametric problem, was first posed by Galileo in 1638. But it was solved by Bernoulli in 1696. So what is this problem? Basically, this is a problem of determining a curve when a body falls under the influence of gravity. Suppose here this is x-axis, and in this case we are considering y-axis downward x, and this is origin, and this is one point A, and here is point B. Then from point A to B, the body can fall under the influence of gravity. It can go down vertically, or it happens only when the point is immediately below A. But there are several other possibilities to arrive at this point under the influence of gravity. So we have to find the curve along which the time of travel from point A to B is minimum. Means here you have to minimize the time. In this case, you have to find a curve along which the distance between 2 points is minimum. And in this problem, you have to find a curve along which time of travel from this point to this point under the influence of gravity is minimum. Under the influence of gravity is minimum. So this problem is called as a very famous problem in calculus of variation. This is the Parametric problem. Now the third problem, in the same manner you can have here, the third one is also an important problem, that is called the isoparametric problem, and it's a very old problem in calculus of variations, and it was generated from some isoparametric inequality. But here isoparametric problem, in general you can state, among all closed curves of a given length L, find the curve that encloses the greatest area. So means here one constraint is given. Suppose you are having several curves and their length is L. It can be like this, maybe length is L, I don't know. It can be the length is L. But if you look at the situation, which curve encloses the maximum area, you have to find the curve of given length which encloses the maximum area. So this is the isoparametric problem. So these are some fundamental variational problems here. So next is the necessary condition for the existence of an extremum in a variational problem. Existence of extremum means in the problems described earlier, here there were two problems. First one was the minimization problem, where we had to find some curve along which the distance between 2 points is minimum, and here was the minimization of time, and here was the maximization of area for a curve of given length. So the problem can be of maximization and problem can be of minimization. So in general here we are calling it as a problem, we are calling it as an extremum. It can be minimum or maximum. So mainly this problem, this condition here, we are calling it as the Euler's equation. We are calling it as Euler's equation. And the statement is, and this Euler equation provides the necessary condition for the existence of an extremum. Suppose this is a functional defined on a set of continuous functions y which has continuous first order derivatives in AB and satisfying the boundary condition that value of y at A is A and value of y at B is capital B. Then the necessary condition for this Iy means this functional, for the existence of extremum is that this yi must satisfy this equation, and this equation number 1 is called the Euler equation, and this Euler equation has the main role in finding the extremum of a given functional. So you should remember this Euler equation for the purpose of the numerical problems, and this Euler equation is going to have several forms in certain conditions. We determine the extremums with the help of Euler equation. Now we conclude that problem of determining the extremals of a variational problem reduces to problem of solving the corresponding Euler equation. Now you see, this Euler equation has some proof, but in this lecture I am skipping the proof. Here I am giving some special cases on this equation. We will discuss the proof in the next lecture somewhere. You see, that was the Euler equation, and in Euler equation the functional was like this. This one means x, y is depending on x, and further y dash is also depending on x. Here x is appearing explicitly, y is appearing explicitly, and y dash is also appearing explicitly. But there can be situations where x is not appearing explicitly, or y does not appear explicitly, or y dash does not appear explicitly in this type of expression. So in those situations, this Euler equation reduces to some simplified form, and we can obtain the desired extremum in a bit simpler way. So the first case here is that where y is not appearing explicitly. Now when y is not appearing explicitly in this situation, so you know that the Euler equation is curly f by curly y minus d by dx of curly f d by dx of curly f over curly y dash equal to 0. But when this capital F is not depending on x explicitly, when this is not depending on explicitly on y, that means this part becomes 0. So that is given over here. When this part becomes 0, the Euler equation reduces to the form that this part is equal to 0. And in this part you can see curly f over curly y dash means this curly f over curly y dash means f subscript means partial derivative of f with respect to y dash. So this can be written in this way. When you see that the total derivative of this is equal to 0, that means this quantity must be constant. So you can directly write like this. So whenever a given functional is not depending on y explicitly, or you can say if in a given functional y is not appearing here explicitly, then the Euler equation can directly be written like this, and it will give you the solution of the problem in a simpler manner. Now we consider the case 2. In this case 2, what happens that this functional
this functional is not depending on x explicitly, because here y and y dash are appearing. Now if we simplify this, the Euler form in this situation, you already know that the Euler form in this case will be like this. Here you have the Euler equation is curly f by curly y equal minus dy dx curly f by curly y dash equal to 0. So in this situation we are trying to solve the left hand side part. So here this left hand side part is written and we are going to solve it. So this thing is as it is, and here we'll apply the concept of total derivatives, and this part is equal to this part. So you can apply the concept of partial derivative. And what is that concept? That if you have a function u of two variables x and y, and you want to find du by dt, then that is curly u by curly x dx by dt plus curly u by curly y and dy by dt. Exactly using the same logic over this fy dash, we find instead of du by dt, here we are finding d by dx of fy dash, and you will obtain this thing. Why? Because in this situation this fy is function of two variables. Fy dash, basically this is function of two variables here. One is y and another is y dash, because x is not appearing here explicitly. So these two things, this concept of total derivative and this thing, will give you this expression. So consequently this thing can be written like this: to partial derivative of f with respect to y, and these two terms are written like this. So this left hand side part of the Euler equation is equivalent to this equation. Now equating this to 0, that gives you the Euler's equation. In the second case, your Euler equation becomes this one. For further simplification, if we multiply this equation by y dash, we multiply this equation by y dash, and then it can be put in this form. This one, dy by dx of this equal to 0. Now if derivative of something is 0, means this quantity comes out to be constant. So always remember, whenever you are given some functional, we have this capital F is depending on y and y dash, and x is not appearing explicitly, then you can consider this equation for solution of the numerical problems. So this was case 2. Now the case 3 is when this in capital F here, y dash is not appearing explicitly. When y dash is not appearing explicitly, then from the Euler equation you definitely know this curly f over curly y will be d by dx curly f by curly y dash equal to 0. When y dash is not appearing explicitly, then this quantity comes out to be 0. When this quantity is 0, then that means curly f by curly y, that is this thing, f subscript y is equal to 0, which is not a differential equation. If you try to solve it, then you will get a function simply y as a function of x. Now the fourth case is that if the functional is of this form, means you can consider this whole thing as capital F, and now in this capital F you can see all the things are appearing. X is there, y is there, and y dash is there. All the things are appearing. So you need to work out on the basic form of the Euler equation. You see, curly f by curly y minus d by dx of fy dash equal to this thing. Now the whole part, that was the a capital F there in that situation. So here you need to work out in the same manner, means partial derivative means this part is corresponding to curly F over curly Y, then dy dx of this part is equal to curly F over curly Y dash. Now we take the total derivative and further simplification gives rise to this calculation. Calculation is very simple, and finally we arrive at this equation. So this equation will be used in some complex problems. So normally our numerical problems are solvable with the help of three cases. Right. So finally, to connect you with the next lecture, you need to know some concept over here. Suppose means here I would like to tell you how to find the length of arc in a two-dimensional curve. Suppose you are having a two-dimensional curve over here, and in the curve is like this, and you are representing this by y equal to y of x. Now suppose you want to find the length of arc between 2 points A and B, and this length of arc is very small, delta s. Now if you draw the line parallel to x-axis here and the line parallel to y-axis here, and you say that this is the right angle. Now for the small length, I say that this distance is delta x and this distance is delta y. And if this is small delta s, then it look like a straight line. Then by Pythagoras theorem, you can say that delta s square equal to delta x square plus delta y square. So when delta s tends to 0, then delta x, delta y also tends to 0, and this expression in the form of differentials can be written as ds square equal to dx square plus dy square, or you can write ds square equal to 1 plus dy by dx square, or you can simply say this is ds equal to 1 plus y dash square under root, and here when you are taking ds square common, so you are having dx square over here, and here you have dx. So that is how you can find the length of small arc between this point to this, length of small arc here. But if you are given the point fix, and these can be at a very large distance, then the formula for the calculation of the arc length of a curve is a to b 1 plus y dash square dx. So always remember. So in the next lecture I would like to mention this formula, and we'll solve the numerical problem with the help of this formula. So that is it for this lecture, and for more problems you can consult this book, and I will also suggest another book where you can look at certain problems. That is a book of Springer publication. I'm going to write the name of the book here. The Calculus of Variations by Bruce Van Brunt, and this is a book of Springer publication. So you can have this book. Thank you.